Hello from ChemHelp ASAP. We're going to do an orbital bonding picture for formamide, and I think the reason why I chose formamide will be clear as we go through this video. Okay, we have a Lewis structure for formamide on the screen. This shows oxygen with its 2 lone pairs, nitrogen with its 1 lone pair, and formamide is a little bit tricky because remember we have an atom with a lone pair, nitrogen, next to a double bond, next to a pi bond, and we said that's a special case in hybridization. And in those cases, that lone pair will want to be in an unhybridized p orbital, meaning that nitrogen needs to have an unhybridized p orbital. Therefore, that nitrogen must be sp2 hybridized. This is not like ammonia. This is a different type of nitrogen. We need a p orbital for that lone pair. So I'm going to draw this structure. I'm going to be probably less correct in terms of the bond angles, because to tell this whole story, we need the molecule drawn in a way that's going to make the sigma bonds less obvious. So we said this nitrogen is sp2 hybridized. So let's put a couple hydrogens off of here. In fact, you can make that hashed if you want, and that more bolded. I'm trying to show this being 120 degrees, but it's not perfect. Okay, well, this nitrogen definitely needs an unhybridized lone pair. And let's assume I've selected the PZ for this. Well, there's going to be a lone pair in this p orbital. And we said that this lone pair needs a p orbital because it's next to another double bond, another pi bond, which means that we want these p orbitals to be lined up with each other. So this carbon needs to also have an unhybridized PZ. It's not a problem because it's sp2, it does have one. But this oxygen as well needs an unhybridized PZ. Now where this picture gets tricky is, what do I do with this hydrogen off the carbon? And I'm going to kind of poke it off in a direction back here. It's hard to place it well, and the lone pairs on the oxygen are also kind of a mess. There'll be an sp2 hybrids, maybe something like this. But the star of the show is really the pi bond and the p orbital. So there's definitely a pi bond between that carbon and oxygen. And now what we see is that this oxygen and this nitrogen and its lone pair in the p orbital are now perfectly lined up with the p orbitals on carbon and oxygen. And this allows for additional interactions, which we will define later. It's called resonance. But this is the special case. Why would a lone pair want to be in a p orbital instead? If there's a double bond next door, well, it allows all these p orbitals to line up, and that's an extra stabilizing effect, again, which we'll call resonance. So we're not quite ready to pull the curtain back on resonance, but when we talk about resonance, we're going to need some of our lone pairs to be in p orbitals. And this is why, because it opens up extra bonding implications, and so, of course, we talk about those implications while we're talking about bonding.